Everyone, welcome to another session of structural analysis 2. So in the previous class we have seen about the introduction of stiffness matrix method. Now we will take down one problem related to stiffness matrix method. Okay, so the question is, analyze the continuous beam shown in figure using stiffness matrix method. Okay, so I'll draw the beam here first. So very carefully observe here. The beam is a continuous beam. The beam is a continuous beam wherein we have fixed support here, and here we have a roller support, and again we have a roller support here, and at this location we have a fixed support. Okay, so here at the center we have one point load of magnitude 15 kilonewton, which is at a distance of 2 meter and 1 meter. It is not at the center, it is 2 meter and 1 meter. Similarly, we have one more point load of magnitude 20 kilonewton, which is at a distance of 2 meter and 2 meter. Then again we have another point load of 10 kilonewton and this distance is 1 meter and this distance is 2 meter, and it is mentioned that EI is constant. The value of EI is constant throughout. The value of EI is constant throughout. Okay, so initially what we do is we try to calculate the stiffness, the degree of kinematic indeterminacy of the structure. So how to calculate kinematic indeterminacy of the structure? See here, whenever we have theta, suppose for example we have theta over here, isn't it? At this location we'll be having theta, and here also we'll be having theta, isn't it? So theta A will exist, isn't it? Theta A will exist. 1 minute. So theta A will exist here in this problem. I'll name this as this point as A, this point as B, and C and D. Okay, so totally in this all the points, theta A will be equal to 0, theta B will not be equal to 0. Similarly, theta C will also not equal to 0. Then theta D is equal to 0. We all know this, right? So how many thetas will exist? Theta B and theta C will exist. So in this condition, my degree of kinematic indeterminacy of the structure is now 2. If theta C existed, then theta D existed, then the degree of kinematic indeterminacy will be again 3. Okay, so totally, since we have only theta B and theta C which is not equal to 0, so then my degree of kinematic indeterminacy will be equal to 2 here. Okay, so now we'll take down another diagram, wherein what we do here is you have to observe here very carefully. I'll draw another beam here. See here, I am drawing another beam here, and this is fixed and this is also fixed. We all know this, right? This is fixed, this is also fixed totally at these two locations. But here at this location at theta B, or at this theta B, at this location and this location, at these two locations, my beam is supported with roller support. Okay, so what we will do here, we will try to rotate this part of the beam. Okay, very carefully you have to observe here. So what we do, we give a small rotation over here. What I am doing here now, I am trying to rotate my beam here. I am trying to rotate this part. Okay, so once you rotate this support, what will happen to the beam? My beam will try to get rotated in this fashion. If I apply clockwise moment over there, now so what happens? My beam will try to get rotated in this fashion, isn't it? My beam will try to get reflected in this fashion. I'll do one thing, I'll draw with the red pen. So my beam will try to get deflected in this fashion. Similarly, at this location, what happens? It will try to get reflected in this fashion. And what I am doing here, I am applying a rotation of intensity. Theta is equal to 1 here. We are applying theta is equal to 1. We are rotating the structure. So what happens here? I am naming this as node 1 and I am naming this as node 2. Okay, these are the two nodes. Whereas this point is A, this point is B, C and D. Okay, so we are rotating this structure now. So what happens here is, you can see here what I will do here. This is 1 1, so I'll write here K11, K11. I'll write here K11 is equal to, so what happens here, I am rotating at B. Okay, so K11 will be equal to 4EI by L when you see from B to A. When you see from B to A, the stiffness will be equal to 4EI by L. Then plus, I am rotating, if you see the span BC, what happens here? Here also 4EI by L for span BC. And then what about joint member CD? There is no rotation for CD, isn't it? If I am rotating theta at B, what is happening? My theta, my this particular node is trying to get rotated, and because of this rotation, span BA and span BC has some deflection, whereas span CD does not have any deflection. Okay, so and moreover, you can see here we have not used any external loads also in our calculation. Only we have used the spans and conditions. We are applying only one radian of rotations to the to the entire non-zero what we say slopes. Okay, so next is once what we'll do, we'll try to solve this one. K11 is equal to, EI is constant, so 4EI by L. What is the span of BA? It is 3, right? So 3 plus 4EI by span of BC is how much? 4, right? You can see there. So what happens to K11? What is the value of K11 now? It is 2.33 EI. Okay, so I'll do one thing, I'll not write here, will create confusion. So K11, once you solve this, you will get 2.33 EI. Okay, you will get 2.33 EI for this one. Now we'll go for K12. Okay, now we'll go for K12. So see here, K12. What is K12 now? I am applying rotation at 1. I am applying rotation at 1 and I am seeing joint C now. If you see the joint C, what is happening for CB? It will be 4EI by L for span CB plus, you can see here we don't have any kind of rotation here. Okay, so K12 will be equal to 2EI by L, not 4EI by L, 2EI by L. Why? Because this is not getting rotated. No, CB, this part is getting rotated, this 50% of the part is getting rotated. But whereas when you consider joint K1 2, this joint, if you consider this particular joint, then what is happening? If you are considering this joint, only this part is getting, this CB is getting deflected, whereas CD is not getting deflected. That is why 2EI by L only for span CB, whereas for span CD it is 0. No, there is no rotation because of this one. So what happens? K12 is equal to 2EI by 4. 2EI by 4, which is equal to how much? 0.5 EI. Okay, so K12 we got the value as 0.5. Here I'll write here K12 is equal to 0.5 EI. Okay, now in the next figure, what we will do, we will try to rotate the another part of the beam. Okay, I'll draw another part of the beam again, once again. So what I'm doing here, you see now, this is our beam, right? Again, this is our beam, and here we have roller support, here also we have roller support. So initially this is node 1 and this is node 2. Initially I have rotated node 1. Now we will rotate node 2 again in clockwise direction. Theta should be equal to again 1. So what happens here is, again once we rotate that one, what will happen? Because of this rotation, my beam will try to get deflected in this direction. Similarly, my beam will try to get deflection in this direction. Okay, so what will happen to K21 at this location? What will happen? K21 will be equal to 2EI by L for span BC, whereas for span AB nothing will happen. This is A, B, C and D, isn't it? So 2EI by L only. So K21 is equal to 2EI by span of BC is how much? 4 meters, right? So K21 is equal to 0.5 EI. 0.5 EI. So we got this as 0.5 EI. Nextly, what we will do, we will try to calculate this value also, that is K22. K22 is equal to, once you are rotating that one, what happens? The same will happen what happened in the previous case, that is 4EI by L for span CB plus 4EI by L for span CD. Okay, so what is the span of CD and CB? So here it is 4 EI by L. So L is how much for span CB? For span CB it is 4 meters plus 4 EI by L for span CD. So for span CD my L is how much? 3 meters, isn't it? So the span of CD is 3 meters. You can see here it is 3 meters. 2 plus 1 is 3. So this is 3 meters. So 4 and 4 will get cancelled. So EI plus 4 by 3 EI will be equal to somewhere around 1.33, right? Sorry, 1.33 EI. So finally K22 will be equal to 2.33 EI. 2.33 EI. Okay. So this is the stiffness matrix we have got. So I will write down all the values. K is equal to my stiffness matrix will go like this: K11, K12, K21 and K22. Okay, So K11, what is the value of K11 we got? K11 is 2.33 EI, isn't it? So 2.33 EI. Then what about K12? K12 we got it as for 0.5 EI. 0.5 EI. Then here K21 we got it as 0.5 EI. Then here also we got it as 2.33 EI. This is our stiffness matrix K. Okay, this is our stiffness matrix we got. So once we got the stiffness matrix, we can now move for our simple calculation of fixed end moments. We'll try to calculate fixed end moments first. Then, so what is the fixed end moments we can get from here? MFAB. So what is fixed end moment of MFAB? MFAB. So we'll try to take down this part downward for our simplification. I'll try to take this part of our beam. Okay. So we'll try to shift this part downward for our simplification calculation. I'll try to take it down here so that my beam will be visible to me. Okay, so this is constant, right? EI is constant. That is what it is written over there. EI is constant, and this is 15 kilonewton, right? 15 kilonewton load. So once we calculate fixed end moments for all these members MFAB, it is WAB square by L square, which is equal to 10 into 2 into 1 square divided by 3 square, which is equal to MFAB equal to minus 2.22 kilonewton meter. Then MFBA is equal to, this is minus, right, because anti-clockwise, plus WA square B by L square is equal to 10 into 2 square into 1 divided by 3 square. So this is equal to plus 4.44 kilonewton meter. Similarly, MFBC is equal to minus WL by 8, which is equal to 20 into 4 square divided by 8 is equal to minus 10 kilonewton meter. Similarly, MFCB will be equal to plus WL by 8 is equal to, here should be minus 20 into 4, it's only 4, right, divided by 8, which is equal to plus 10 kilonewton meter. Then MFCD is equal to minus WAB square by L square is equal to minus 15 into 1 into 2 square whole divided by 3 square, which is equal to minus 6.67 kilonewton meter. And MFDC, it is DC, is equal to plus WA square B by L square, which is equal to plus 15 into 1 square into 2 divided by 3 square, which is equal to 3.33 kilonewton meter. Okay, now what we do here is we'll try to take down the moments, fixed end moments. What are the fixed end moments we have? You can see here, will denote P1 dash is equal to MFBA plus MFBC is equal to 4.44 minus 10, which is equal to minus 5.56 kilonewton meter. Then again we'll take down P2 dash, which is equal to MFCB plus MFCD is equal to 10 minus 6.67 is equal to 3.33 kilonewton meter. So what we are doing here, we are trying to take these moments MFBA and MFBC, similarly MFCD and MFCB and MFCD. Why we are doing that? Because at this location moments will be equal to 0, isn't it? So the same thing, the equilibrium equations we are applying here. To overcome that, we have to add summation, we have to simplify those moments, isn't it? So what we do here is, we got the value of P1 dash and P2 dash. The simple stiffness matrix method calculation is delta is equal to inverse of stiffness matrix into P minus P dash, isn't it? So what is this P? This P will be equal to 0. Why? Because there is no sinking of support. P is equal to 0. Why? Because there is no sinking of support here. So what is the stiffness matrix we have? So once you multiply this one, see here, this is K and this is minus P. So plus into minus, minus here. So I'll write down the stiffness matrix, that is 2.33 EI. Then here we have 0.5 EI. Then here also we have 0.5 EI. Here we have 2.33 EI. This should be inversed, isn't it? This matrix should be inversed. Then into minus 5.56. These are the two values I am writing here, P1 and P2. Then 3.33. Okay, so once you do the inverse of this matrix and multiply these two matrix, what happens is delta is equal to, you will get 2.82 by EI. Once you do inverse, this EI will go in denominator. Then this is 2.82 EI. This is minus 2.07 by EI. So that is theta B is equal to 2.82 by EI and theta C is equal to minus 2.07 by EI. Okay. So once you get theta B and theta C, we can simplify this one. We can easily apply these values in our MAB and MBA. That is capital MAB is equal to, we have the formula MFAB plus 2EI by L into 2 theta A plus theta B, isn't it? So once you substitute these values in the equation, we have MFAB, which is minus 2.22, we have calculated just now. Then plus 2EI by span of AB is 3. Then theta A will be equal to 0. Then theta B value we got it as 2.82 by EI. So simplify this one, you'll get the value of MAB. MAB is equal to 0.34 kilonewton meter, which is minus. Okay. Similarly, you'll get the value of MBA, then MBC, then MCB, and then MCD finally. So these are all the values you'll get for the final moments. Okay. This is how we calculate. So finally MBA, you'll get it as 8.2 kilonewton meter. Like we simplify this one, you will get all the values of unknown moments. Okay. This is how we calculate the value of unknown moments with the help of stiffness matrix method. So once you go through the calculations, it will be easy for you. And these are the steps which are involved. Each and every step is important, which I have given you in the previous class. Okay. So in the next class, we'll try to take another problem related to stiffness matrix again. Okay. So as of now, this is the problem. This is the basic problem. later on we'll be having some more important problems which will be somewhat different from this procedure. Okay, method will be same, matrix will be same. The only thing is the calculation part, this part especially, this part will be slightly different, this p and p dash. Okay, thank you.